Yeah, our time is very close. So, okay, so please start your talk. Thank you. Yeah.
So, hello everybody, so my name is Sylvain, and today I'm very happy to be there in Japan after Korea, and I am very happy to present to the work we have done during the last 3 years after my PhD about brain-computer interface based on median nerve stimulation, and how is it possible to use median nerve stimulation both to increase BCI performances but also predict BCI performances. So first of all, I'm particularly interested about brain-computer interface based on cerebral motor activity. So as you can see from this picture, the idea is to record the user's brain activity, usually using the EEG technique, and then the user tries to perform mental imagery tasks. So for example, motor imagery, left hand and right hand motor imagery, that we will try to detect using feature extraction and classification steps. And thanks to the steps, the BCI will provide the feedback to the user. So in this case, it was a visual and haptic feedback in the same time. So when we talk about brain-computer interface based on cerebral motor activity, we can really often talk about motor imagery tasks. So in the literature, we can distinguish two kinds of motor imagery tasks, visual motor imagery and kinesthetic one. And the last one, the kinesthetic motor imagery task, is very interesting for BCI, but complex to perform for the user. It's complex because it consists of recalling feeling and haptic sensation felt during the real movement, but without executing it. And why the kinesthetic motor imagery task is very interesting for BCI? Because it activates the primary motor cortex and additional motor areas in the same way as during a real movement. And basically, during the kinesthetic motor imagery of the right hand, for example, you will have a contralateral activation of the motor cortex at the cerebral level. And when we talk about motor cortex activation during kinesthetic motor imagery task, we can also describe it in terms of ERD and DRS patterns. So in terms of modulation of power comparing to a resting state or baseline. So those motor patterns were introduced by Fauchellers in the 90s. So basically during a motor task, you have a decrease of power comparing to a resting state, which appears in mu and beta frequency band, so between 8 to 30 Hz band. And after the motor task, you will have an increase of power called ERS phase or beta rebound, because it mainly appears in the beta frequency band.
And excuse me that I interrupt you.
Yeah.
This is true for Cephis EEG, but if you take invasive, I think mechanism is different. No?
Yeah, it's possible that in invasive the mechanism of ERD
just opposite.
Yeah. Not sure about that. I think.
Okay, I'm so sorry. So okay,
no problem.
I'm not sure.
But maybe
it depends. I think in ECOG, ECOG is the same. Maybe if you look at single unit, it's different. Yeah.
Yeah. So interestingly, during kinesthetic motor imagery task, you have the same kind of motor pattern. So a decrease of power during the kinesthetic motor imagery and increase after the kinesthetic motor imagery task. So we can use it in BCI to detect motor intention and motor imagery from users. So now let's talk about the main problematic in the BCI domain related to poor BCI performances. So Fabien already mentioned that, but we all remember the Allison's paper about BCI literacy and the fact that between 15 to 30% of people are unable to use the BCI. They cannot use the BCI for many different reasons, but here are some examples of why. The first one is the low accuracy. So for example, to discriminate two different motor imagery tasks, left hand and right hand, or left hand or on resting state, for example, in average, we have 75% in terms of accuracy. It's quite low considering clinical application, for example. The second reason is the high variability. So intra-variability, but also inter-variability. So we have a lot of variability from one subject to another, but also for the same subject for different sessions over time. And we have a lot of variability both for several motor patterns generated by the subject, but also in terms of BCI performances. And finally, we have to think that in most of articles from the literature, we are in the best condition. We are often in laboratory control environment with asynchronous BCI, meaning that the subject doesn't perform the task when he wants to, but when the BCI has to do so with a visual signal or sound signal. So what I propose to try to solve this problem is to develop a new paradigm of brain-computer interface based on median nerve stimulation. So what is median stimulation? Is okay, I have a bug. It's not possible for me to. Okay, median stimulation. So what is median stimulation? Is just an electrical low stimulation just there at this location between the two tendons. It's not painful for the subject. It's totally non-invasive. And when you stimulate the median nerve, you will generate micro reflex movement between the thumb and the index like that. So each time you will stimulate the median nerve, each time you will stimulate a micro-passive movement. And over the motor cortex, you can also generate ERD and DRS pattern after the median stimulation. So you can see that on the red curve. After the stimulation, you will have a decrease of power, very short, very quick decrease because the stimulation is discrete. And after the ERD phase, you will have an ERS phase or beta rebound. So now the question I would like to ask is, what's happened if you stimulate the median nerve in the same time that you perform a motor imagery task? Because at the same time, you will have an ERD from the motor imagery task, and at the same time, you will have an ERS from the median nerve stimulation task. And in theory, it's not possible to have at the same time ERD and DRS, considering the gating process theory. So we conducted an experiment to try to study that. And what we show is that if you stimulate the median nerve at the same time that you perform a motor imagery task, at the end, you will have a large ERD. At the end, you will have an abolition of the ERS pattern from the median nerve stimulation task. It's quite logical because it seems that the ERD from the motor imagery task seems to be prioritized comparing to the ERS from the median nerve stimulation task. And it's quite logical because ERD represents more an activation of the motor cortex. So it seems that the activation of the motor cortex seems to be prioritized comparing to the ERS from the median nerve stimulation task. So those findings were very interesting because we can try to build a new kind of brain computer interface based on median nerve stimulation with two different classes, median nerve stimulation alone and median nerve stimulation during a motor imagery task. And if you do that, we show that we have at the end 21% improvement in terms of accuracy to detect kinesthetic motor imagery task, comparing to a more classical BCI based on kinesthetic motor imagery versus resting state. So if you use median stimulation, you improve your accuracy in average in 21% in terms of accuracy. So it's for our database. So we can imagine a new BCI like that. The subject will perform the motor imagery task when they want to, and in parallel, we will stimulate the median nerve each 3 or 4 seconds. And after each stimulation, the classifier will just analyze if there is an ERD or an ERS. If there is an ERS pattern, it means that the subject is in resting state, and the ERS for the median nerve stimulation task could appear. But if there is an ERD, it means that the ERD from the motor imagery task hits the ERS from the median nerve stimulation task. And we believe that this new BCI could be very, very useful for 3 different reasons. So first, the usability, because with this kind of BCI, the subject will perform the task when they want to, and not when the BCI asks to do so. We already show that with this kind of BCI, we have an improvement in terms of accuracy, so in average 21%. And we also think that it could be better synaptic plasticity, because if you stimulate the median nerve in the same time that you perform a motor imagery task, in the same time you will have a motor cortex activation and a somatosensory cortex activation. And some of the articles in the literature show that in this case, you will have an increase of synaptic plasticity. So it could be very useful for stroke rehabilitation or sports training application, for example. So just a figure to show what's happened for different classes. So at the left side is motor imagery with median nerve stimulation, on the right side, median nerve stimulation alone. So just at the beginning. So now, at the left side, the motor imagery will start. So you will have a contralateral ERD, okay? And at this time, so just in a few seconds, you will have the beginning of the median stimulation. So now at the left side, you will have ERD at the contralateral side. And there, here you can see that you have ERS against ERD. And it's why if you use median stimulation to classify, it's very easy for the classifier to detect which class is it, because you have ERD against ERS. So now we use this kind of recompense interface based on median stimulation for two different applications. The first one is to try to detect intraoperative awareness during general anesthesia. So it was the topic of my thesis. Some of patients have a recovery of consciousness during or general anesthesia and during the surgical procedure. So it's very traumatic for patients. So we try to detect that. And there are no sufficient method in the literature to try to detect intraoperative awareness. So we propose to use BCI and BCI based on median estimation to try to detect motor cortex activation, because the testimonies from patients who suffer to intraoperative awareness was okay. I tried to move to warm the medical stuff, but it was not possible due to the pluralization during the surgical procedure. So it's a possible application. And another project we just started a few months ago is about the prognostication for coma stage patients. So we will try to use this kind of BCI to detect different altered state of consciousness for coma stage patients. So now, in the first part of my talk, I showed why brain-computer interface based on median estimation could be very useful in terms of accuracy, so to increase BCI performances. But now I will try to show you how we can use it to predict BCI performances. So if you use brain-computer interface based on median estimation, at the end you will have two different classes. So first, median estimation alone, corresponding more to resting state in a classical BCI. And the second class is median estimation during motor imaging class. The question I will ask today is, can we extract some information from the user considering just this class of passively stimulation of median estimation? So in other terms, if I passively stimulate the median nerve of a subject, is it possible in analyzing ERD and DRS pattern after median estimation if this subject is good or bad with the BCI? So it could be very useful for BCI community, for example, to adapt the threshold to maintain high level of motivation for subjects, but also to harmonize a study population before an experiment. For example, if I want to understand more why good performers are good, maybe I would like to select only good performers in a BCI experiment. So in this study, we will try to check three different questions. The first question is there a correlation between ERD feature after the median stimulation and BCI performances? The second question is, can we use this ERD feature after median stimulation to predict BCI performances? And finally, can we try to predict the group level of motor imagery BCI expertise with median stimulation? So for this experiment, we had 31 right-handed LC subjects. We recorded the EEG with a biosemi amplifier with 128 electrodes, and we had only two different motor tasks, so median stimulation alone and median stimulation during a motor imagery task, so during 2 seconds of kinesthetic motor imagery task. So for the result, we first compute the time frequency map with EEG lab, so in terms of ERSP, so event-related spectral perturbation, for both motor tasks. So for motor imagery tasks, we can see that here we have a large ERD in the mu and beta frequency band. For the beta frequency band, we have two separated ERD, but it's in adequation with the literature for this kind of task. And after the motor imagery task, here we have the beta rebound, mainly in the beta band. So now for median nerve stimulation task, we can see that we have three different motor patterns. The first one is the PSR, the post-stimulation rebound. So at the moment of the stimulation, we have a big ERS, and it's due to the activation of the afferent way during the median stimulation. After that, we have the ERD phase in mu and beta frequency band I previously showed during the introduction. And we will use this ERD to try to correlate the ERD with BCI performances after. And after the ERD phase, we have the beta rebound, and you can see that this beta rebound is stronger comparing to motor imagery tasks. So we also compute offline BCI accuracy using different frequency bands and using Riemannian geometry and tangent space with logistic regression. And we can see that the BCI performances in merge mu and beta frequency bands, so between 8 to 30 advanced, is stronger comparing to other one. So now we compute the correlation between ERD feature after the median estimation and BCI performances. And what we show is that we have a very good negative correlation between the ERD feature after the stimulation and BCI performances. We have a negative correlation. Why? Because stronger is the decrease. So stronger is the decrease of power. So stronger is the ERD, better is the BCI performances. To compare this result we obtain with the literature, we can see that we have a correlation of 0.71. We can compare with the SMR predictor of Blanquer's or PP factor or spectral entropy. And if we compare about other neurophysiological predictor, we have a better result with median estimation. So now the question I will ask is how many stimulations are needed to have significant correlation? Because here for this correlation, we use all the trials, so more than 50 trials. Finally, to respond, not so much stimulation are needed. We show that only with 20 stimulation of the median nerve, we could have a significant correlation. So it means that if you stimulate the median nerve every 3 or 4 seconds, after 1 minute of signal before your experiment, you can have significant correlation. So the other question I would like to ask is, can we predict BCI performances using median estimation? Because just before I showed significant correlation, it's very good result. But in a lot of articles, you can see very good correlation, but when you try to predict, it's not possible. It's not so, the results are not so good. So we try to do that with the lasso model, and we show that in this frequency band, so mu and beta frequency band merged together, we have a correlation to predict BCI performances using ERD after median estimation. We have a correlation of 0.61 with an error of 9%. So it's a good result, but you can see that it's not working for very bad subject and very good subject. So what we try to do after that is try not to exactly predict the BCI performances, but more the BCI, the motor imagery BCI expertise in terms of group level. So we conduct a new analysis to do that, and we separate our 31 different subjects in terms of group level of BCI expertise with low, medium, and high performers. So we conduct an analysis with 3 different groups or 2 different groups. So first we compute the ERD in terms of topographic map to see if there are some difference in terms of ERD. And we can see that for high performers, we have stronger contralateral ERD for both tasks, for the 3 group analysis and for the 2 group analysis. So it's quite logical. It's in adequation with the literature. And when we try to train different algorithms to try to detect if a subject is low performers, medium performers, or high performers, we can see that we can detect with pretty good accuracy, 74% if you are low or high performers. But when we conduct the analysis with the 3 groups, it's not significant. So the result seems to be bad. I think it's mainly due to the low number of subjects in this database. We have only 31 subjects. So to conclude about this work, we found a new neurophysiological predictor based on median estimation. So if I stimulate the median nerve and I take 200 milliseconds, between 200 milliseconds and 800 milliseconds after the median estimation, we have a strong ERD, and we can use it to try to predict BCI performances. In my opinion, it asks a very relevant question about neurophysiological predisposition for subject to use a motor imagery BCI. If we compare with the literature, the neurophysiological predictor based on linear stimulation could be very relevant. What we want to do in future works is not only use ERD patterns after linear stimulation, but also ERS patterns. So which we already test with ERS patterns. The correlation is not so good, but maybe for some subject it could be better with ERS pattern, and for other subject it could be better with ERD. So we will try to compute ERD and ERS pattern to try to predict BCI performances. And finally, we would like also to compute all the neurophysiological predictors in the literature. So the spectral entropy, the PP factor, the SMR predictor from Blanquers with the predictor based on linear simulation to try to have like a gold standard of neurophysiological predictor together. And just one word to say that we have a lot of recently funding about BCI based on linear simulation to different projects. And we are now looking for postdoc students. So if some of you are interested about that, don't hesitate to tell me or to talk with Fabien. And we have also 2 different workshops we will organize at the MPC conference and BCI meeting so in June about altered state of consciousness on general anesthesia and BCI. So you are welcome. So don't hesitate to come. Thank you for your attention, and thank you for my team and my collaborators.